Okay, so let's discuss few more aspect about the sliding mesh, but now we're going to use the release version, that is OpenFOAM 30x. Okay, so few settings is almost same for what we look at for OpenFOAM extended version, but couple of things here is changed, like cyclic AMI and compared to the GGI. Okay, so few things is changed, otherwise everything is same. So same tutorial you can try for extended version also, and the extended version tutorial you can try with the open release version as well. But let's closely look at different entries that is applicable to both version. Okay, it's not only restricted to the OpenFOAM 30x, but you can see for all different class of version of OpenFOAM similar class of the entries is available. So let's look at few entries in the dynamic Dict file. Okay, so this file basically allow us to mimic the all the topology change and the mesh motion change. Okay, so mesh motion and the topology change are handled by the dynamic mesh functionality in the OpenFOAM. Okay, in the broader sense if we see. Okay, so let's look at few basic aspect. Okay, and then we go towards the few more detailed tutorials. Okay, so the dynamic mesh functionality allow us to take into account the mesh motion and the topology change. Okay, setting for dynamic mesh are described in the dynamic mesh dict files, and this file is located in the constant directory. So whatever the mesh motion related setting you want to do, all the things goes inside the dynamic mesh dict file, and that is available in the constant dictionary file. Okay, solver that can handle this mesh change has a letter DYM. Okay, so like pimple DYM form, inter DYM form, ICO DYM form. So DYM is nothing but coming from the dynamic mesh. Okay, so that is the short form of dynamic mesh. So from there it is coming as a DY mesh form. So whatever the solver, if you see with the word DYM, you understand that that particular solver is capable enough to take into account the mesh motion into the solution algorithm. Okay, so that is how one can distinguish normal solver with the dynamically enabled solver. Okay, available type of dynamic mesh without topology change. Okay, that is static mesh FV motion available. So disable the dynamic mesh motion. Okay, then solid body motion FV mesh. Okay, so that allow you to look at the rigid body motion such as translation, rotation, movement, all these things you can take into account inside of this. Okay, so that is also available. Then multi solid body motion, here you have a single solid body motion, in the similar line you have multiple solid body motion. Okay, so nothing but at a time two rotor is rotating in the same domain, multiple rotor is rotating in the same domain. So like that way you can take into account the multiple solid body rotation. Then dynamic motion solver. Okay, for a Laplacian equations, so what it going to do, it try to solve a Laplacian equation for the motion displacement or motion velocity to calculate the updated position of the points. Okay, so based on the provided mesh motion on the any of the patches, what it going to do, it try to solve the Laplacian equation for motion displacement or motion velocity, and then accordingly try to update the points. Okay, so that is what going to happen here. Then dynamic inkjet FV mesh, so move mesh points sinusoidally in the x direction by explicitly calculating the new position. So that is a dedicated FV dynamic inkjet FV motion available for something like a piston cylinder motion or something like push motion in the sinusoidal way, it is available. Then dynamic refine the mesh depending on the user specified field variables. Okay, so depending on the, let's say piston is moving and some layer is refining and some layer is coarsening, we can add the layer, we can remove the layer. So this thing is possible under this umbrella. Okay, so this is few options is available under the dynamic FV mesh without topology change. Okay, now if we look at out of it couple of the things like solid motion FV mesh. Okay, so when we talk about the solid motion FV mesh, so it has a different type of solid motion possible. One is the translation motion and the rotational motions. So when you talk about the translation motion, you have linear motions, uniform linear motion with the constant velocity. That means either patch or entire domain is moving in one particular direction, like oscillatory flows. Okay, so uniform linear motion, not oscillatory, in only unidirectional velocity. You can specify one patch unidirectional velocity in moving with that particular direction. Oscillatory linear, that means you have a piston and cylinder class of the motion where it go forth and come back again. Okay, so that class of motion is possible in terms of the translatory motion. Then in terms of the rotational motion, you have a rotating motion, uniform circular motion. So with respect to one particular center or the axis, entire, let's say, rotor is rotating. Okay, so it's rotating motion. Axial rotating motions, uniform circular motion, same, but in previous case you have to define the axis, and here you need not to define the axis. Whatever the center of that, it automatically take into account that part. Okay, then oscillating rotating motion, like it rotate with respect to axis, but it's not going to rotate 360 degree. Okay, it goes till 45 degree, again come back to center, again goes in the clockwise, anti-clockwise, 45 degree, if you want to look at like some class of, let's say, washing machine. Okay, so washing machine drum never rotate in entire 360 degree. Okay, but some mixture always rotate in the 360 degree. So if we want rotating oscillatory, like the washing machine drum, okay, it rotate some degree clockwise, anti-clockwise, clockwise, anti-clockwise, then we have to take into account this class of the motion. Okay, then SDA, SIP design analysis, so dedicated some type of dynamic mesh motion is available, like rolling, pitching, yaw, all this take into account in SDA, SIP design analysis based particular topology variation is available. Then tabulated data, so you can specify the tabulated 6 DOF motion as well. Okay, with respect to time, how the motion is varying, you can define in terms of the tables. Okay, so you, if you have some predefined table, you can utilize it and try to work with that. That is possible. Then combination of above type of the motion, that means if you want to look at multiple motion at a time, you can go with this multi-motion options. Okay, but if you want to look at the different class of motions and its available options, then we can quickly check in terms of this particular web page. It is very nicely defined, so many things here. Okay, so let's look at, so in on this web page you will see so many different parameters that allow you to set this solid body motions. Okay, so this give you very detailed explanation of all each and everything, like example, simple interface. Okay, so dynamic FV mesh, solid motions, and you can define the parameter. Then variation of the multi-body motions. Okay, so we have multiple bodies like body 1 and body 2, and you can define the different parameter based on the different bodies. It is possible. Then different functionality available, like as I told you, axial rotating motion, constant velocity rotating motion, linear motion, constant linear velocity, oscillatory linear, then oscillatory rotating motion, SDA, motion specific marine ship, 3 degree of freedom ship motion is available, then tabulated, then multi motions. Okay, so when we talk about axial rotating motions, okay, then certain options available, like you have to define as a dynamic FV mesh with the solid body motions. Okay, and what else you require this solid body coefficient. So this all entry goes where? This all entry goes inside this one file, dynamic FV mesh, and this file is located inside the constant folder. Okay, so don't forget that part. And here when we talk about, let's say, rotating motions, and axial rotating motion, we have to specify the cell zone that is rotating. Okay, like in the previous cases we defined the rotor or the particular cell zone that is rotating, so we have to identify that rotating zone and say cell zone rotating. Axial rotating motion is the type of the function, and for that what we required, origins, okay, and radial velocity. So vector we specify how it is rotating and it is set. Okay, cell zone, so cell zone ID is the name of the cell zone designed during the meshing operations. So like we have to either create at the blocking level, or if you are importing the mesh from the external mesher, then define the rotating zone as a separate zone, and then you have a connect in between interface, and that interface will be taken care either GGI or the cyclic AMI. GGI when if you work with the extended version, cyclic AMI when you work with the release version. Okay, like use this process. So use this to specify subdomain of rotating turbo machine or propeller type of the things. Okay, so where we have a rotor is rotating and the stationary object, we have to specify the origins. Okay, origin of the rotation, this will be rotating points. Okay, or or through this point the axis is going to pass out. Okay, then radial velocity. So this is a rotating speed of any domain specified as a 3D vector. This is not a unit vector. Okay, and in which directions ultimately it's with respect to what it is rotating, you can specify magnitude of vector in the speed of rotation. The component direction of vector specify direction of your rotating axis. Okay, so if it is rotating with the z axis, you can specify here. If it is rotating with the x axis, you can specify here. Okay, and it is rotating in the total rotation 360 degree. Okay, then you have a few degree per second. Look, so 360 degree per second, the unit of input of not entirely clear. Some example of source code suggests that input is in the degree, but some source code suggests in the RPM. So explicitly there is a distinction in between. Okay, so we explore when we try to look at its actual tutorial. Then we have linear motion. So for linear motion we have to use the cell zone that is moving with the particular velocity, and again functionality is the linear motion. Okay, and linear coefficients is required for like velocity. So we can say the entire this is moving in x direction by 1 meter per second and in the z direction 0.25 meter per second. This is the cell zone ID. Okay, and then velocity. So cell zone ID is the name of the cell zone during the meshing, whatever we specified. Okay, use this to specify subdomain if you have a linear motion to adjust a single portion of the domain. Okay, if you, let's say entire domain is moving, then no need to specify anything. If you wish to move the entire domain, then specify none or do not include this parameter. That means either you remove entire line or say cell zone equal to none, then entire domain is going to move in with this velocity. Okay, so velocity vectors in x, y and z direction. Then you have oscillatory linear motion. So when you have oscillatory like piston and cylinder, okay, so again functionality is oscillatory. Okay, amplitude you can define in x, y, z direction, and the frequency you can define. Okay, so that is how you can control the amplitude and frequency in particular directions. Cell zone amplitude. So amplitude of the linear motion amplitude provided as a 3D vector definition. So if you want to look at motion in only x direction, specify this rest are 0. Okay, so total magnitude vector provided a magnitude of the domain. So like that way you can specify what is the magnitude with which the domain is oscillating. Okay, and here this goes in radian per second. Okay, so this is frequency of oscillation, linear motion with oscillation at this frequency. Okay. Then oscillating rotating motions. So here we have a origins above which it is rotating, then amplitude, okay, unit in radian, and then the omega unit per radian per second. So again rotating zones, if entire domain is rotating, no need to specify that. Okay, then origins like single SRF, where single reference frame where entire domain is rotating. Okay, where you need not to specify this. Let's say entire domain is rotating, so this line is not applicable. Okay, then origin of rotation, this is with a rotating point, so through this the axis of rotation going to pass out. Okay, so that is what you can see. And then this is amplitude of rotating motion. Okay, so you can control the amplitude, you can specify the individual component whatever you required. Okay, then rotating motion, so it is rotating with respect to origin and the axis, and the radian per second is omega. Okay, so all this description is given very nicely in this particular web page. Okay, SDA is the motion specific to modeling the marine application. SDA creates prescribed motion in the 3 direction: rolling, have and show, or roll, pitch and yaw. Okay, this was intended to simulate the motion of a vessel in a subway. Okay, so if you are interested to look at the any type of this class of motion, then you have to look into this particular thing. Okay, so that is one thing, it is available. Okay, so you can specify certain things, like if you want to look at, then we say functionally SDA. Okay, CG we want to specify, then few more rolling, max min. Okay, so have max min, and then tip. So many different parameters available, like model scale ratio. Okay, I never use it. Okay, but some description is available, so if you are interested, then please go through it, and entire detail of everything is provided. So if you are interested, okay, try to look at how exactly they set up things. So they define everything. Look, reduce the square root of scale factor TP, okay, TPN, rolling maximum parameter. So this is a very specific movement, okay, and it is specific to the some type of the ship motion or that regard, okay. So if you are interested, please try to look at in detail. It is provided here, okay. Then tabulated 6-degree DOF, okay. So here in place of specifying the any mesh motion, you can say your CG of CO of G, okay. So that is nothing but your body's center of gravity, and it is location you specify, and then you can define the entire data as a data file, okay. So example of data file is something like this way. So with respect to that, if your linear displacement or rotating vector, you can specify at a 0 time, this is you have, and rotating is something like this way. So you have to generate all these motions, okay, and use tabulatedly you can specify, and based on that it going to work. Then multi motions, so at a time you can define the multiple motions, okay, or you can define the multiple solid body motions, or within the one solid you define the multiple motion as well, okay. So few options is available here, like different motions at a time you can set, okay, and it's combined way it going to work and give you the final motion. So this is all in detailed way available on this web page. So if you are interested, try to look at this Wikipedia, okay, and try to check different entries and different options. So few of the examples I am noting down here. Let's say linear motion if you want to look at, okay. So then we have to specify nothing but solid body FV mesh as a dynamic FV options. Library by default goes. Then we have to specify solid body FV mesh coefficients. In this you can say functionality as a linear motions, and then we have to specify linear motion coefficient in terms of velocity. If you working with the oscillatory linear motions, okay, then what is the cell zone that is going to oscillate, you can specify that, and amplitude and the omega. So it going to look at only in the y direction this oscillation. Rotating, then same way, axis of origin, then axis of rotation, and then the radian per second its value. Axis of rotation, so that axis of rotation you can specify the origin, and with this it try to rotate with respect to z axis. Then oscillatory rotating motions we can look at like this way, okay. Then we have a tabulated functions. So as I told you, you can define with the help of particular tables, so that entry. Then multi motions, okay. So let's say one rotating zone, it is like rotating motions, and along with that you have oscillatory rotating motion as well. So you can combine both the things and finish the multiple rotation at a time for the single object, or you have a different rotor, that is also possible with the multi solid body motions, okay. So look, there is a difference, okay. Multi motion, it's belong to the only one cell zone, and you with that cell zone, either the cell zone is rotating as well as moving in the linear direction. Cell zone is linearly moving as well as it is oscillating. So that is one cell zone. Over one cell zone you have multiple functionality, that is called multi motions. And then you have multi solid motion, where you have different class of cell zone available, like rotor 1 and rotor 2, and over that different cell zone you have to specify the functionality. So both is different. One is the multi motion, so for a single cell zone you specify multiple motion at a time, okay, either translation, rotation, oscillatory, linear, anything, whatever you want to do that. And there is a multi solid body motion, where at a time two different solid body is rotating or linearly varying here and there, okay, or you can specify whatever the motion you want, okay. So that is also available. So depending on your requirement you can check the different thing, okay. Then so this is all options available under the solid body motion. So we have a solid object, either rotor, stator, or some linear object moving in the one particular direction. Let's say bullet is going with the one particular velocity in one particular directions, okay, or piston and cylinder oscillating, okay. So this is come under the solid body motions, okay. So for that you have a different couple of options. So here we showed you something like 8 different examples, okay, and we try to simulate a couple of them. Okay, then in the mesh motion you have a dynamic mesh solver FE options available, where some of the boundary is only moving here and there. Okay, not entire cell zone is moving. Okay, in that regard, let's say one of the patch is moving in one particular directions. Okay, so in that regard we have to rely on the dynamic FE mesh motion. So we solve this with the FE 4, but let's explore couple of entries here. So what we going to look at when we going to solve this? So what we solve is solve a Laplacian equation for a motion displacement, that is dm, okay, or motion velocity, that is um. Either we solve for displacement equation or the motion equations, and when we are solving we have this diffusivity, okay, gamma. So this diffusivity, so this is Laplacian, and then if you have a diffusion term. Okay, so basically it is something like this way. Okay, so so we have a, either depending on motion displacement we can solve the equation, or the motion velocity we can solve the equations. Okay, user can select which equation to solve. Okay, and depending on the selection of this diffusivity coefficient we have different variation available here. Okay, so let's look at, in this umbrella you have a couple of options like displacement velocity. Okay, so when we talk about the displacement velocity, what it going to do, it try to look at the how this mesh motion is displaced with the help of this displacement options. Okay, so it is called the displacement velocity base, and when we talk about displacement velocity base, some different file supposed to be there inside the time folder, like point displacement type of the new file we have to kept inside the 0 folder, and based on this point displacement we have to specify the displacement options. Okay, and either the patch is rotating, moving, whatever we want, we have to specify in the point displacement particular file, and that file we have to kept inside the time folder. Okay, and how we going to select? Solver is the displacement Laplacian solver. Okay, so displacement of Laplacian, so that is mean Laplacian of displacement we going to solve. Okay, that is the solver name. So, and here we have to specify the diffusivity. So this diffusivity is the diffusivity of the Laplacian equation, and for diffusivity we have a couple of options available that we already explored. Okay, like inverse and the uniform, okay, non-uniform, exponential, couple of options available. Depending on that, or depending on the mesh motion and the mesh configuration, we have to tune this diffusivity parameter, and move is the moving patch name. So whatever the patch name is moving, with respect to that it try to look at the inverse distance. Okay, and try to calculate. Then second option, velocity component Laplacian, so that means this motion velocity we're going to solve this particular equation in place of this. Okay, when you say it is a displacement Laplacian, you're going to solve this equation. When you say velocity Laplacian, that means you're going to solve this particular equation. And when you are working with this velocity Laplacians, okay, at that time we require the point motion ux. Okay, so velocity Laplacian, you have two options. One is velocity Laplacian, and then one another called the velocity component Laplacians. Okay, so velocity Laplacian, when you say we try to solve entire this equation, there is a component wise this equation, that means we try to solve only x component of this motion velocity. So that is the velocity component Laplacian, and in that when we solving component Laplacian we require the point motion of ux, this new file in the time folder. If we work with the displacement Laplacian, then we require the point displacement new file inside the our particular time folder. But when we work with the velocity component Laplacian, this file required. All other setting remains same. In place of here we require the x component, y component, z component. Okay, and then we require the again the diffusivity different parameter. If we work with the velocity Laplacian, we're going to solve these equations. Okay, and for that also we require the quantification of diffusivity, and when we work with this we require the point motion u. Okay, if we work with the component Laplacian, we require point motion ux file inside the time directory, that is inside the 0th folder. Okay, but when we work with the velocity Laplacian, point motion u file required inside the time folder. So what different solver we are using, depending on that different files we have to put or kept inside the 0 folder. Okay, so and now let's look at the option that is available for diffusivity. For diffusivity, okay, we have different class of options available. Before that, for under this umbrella you have different another options like velocity Laplacian, velocity component, then you have a displacement layer motion, displacement Laplacian, displacement interpolation, displacement component Laplacian, SRB. Okay, so couple of few more equations based solution available, and for that we have to look at different options. But this all the solver options available, depending on what class of the solver you are choosing, it try to simulate this or these equations, and for that we require certain parameter like diffusivity index. Okay, so for diffusivity we have a certain options available like this way: uniform, directional, okay, multi-directional, okay, inverse distance, inverse phase distance, inverse point distance, inverse volume, quadratic exponential. Okay, so depending on the mesh motion and the mesh configuration, we have to tune this particular options, and so it is no any rule is available that for this class of motion this give you the better result, because when you change the mesh configuration or the domain size, it's going to change completely. Okay, so when you are starting a new project, try to tune this parameter nicely, otherwise mesh motion going to fail. Okay, so be careful with this parameter. So depending on your mesh motion, you try to select first the solver options. So here is different solver options, and then for each solver option different class of parameter available, couple of required this diffusivity concept. So you have a different class of diffusivity options available to try to tune this, and based on that it give you the different idea. Okay, then as I told you at the beginning, we have dynamic inkjet FV motion options available. Okay, so first understand this thing. When I say solid, okay, start from here. When I say solid body motion FV options available, what it mean? It mean that dynamic FV mesh is going to solve with the solid body FV mesh motion. Okay, when I say this dynamic motion solver FV available, what it mean? Dynamic FV mesh is going to solve with the dynamic motion solver FV mesh. Okay, under this you have a couple of options. Okay, similar line, when we talk about inkjet, dynamic inkjet FV motion, that means at the dynamic FV motion we have these options available. And when we talk about this, it is nothing but something like a pumping system of the injector type of the things. Okay, set of point in the pumping region are compressed or expand sinusoidal to impose a sinusoidal variation of the flow at a nozzle exit. Like let's say we want to look at the synthetic jet. Okay, so membrane is oscillating in particular direction up and down. Okay, so if you want to mimic that class of the thing, you can use this class of the particular FV mesh options. Okay, that try to mimic the same thing like oscillatory type of the things. So for that you have a amplitude, frequency, and a reflex x. So this is the point through which the mesh motion going to affect it. After that it not going to affect. Okay, so when we solve the particular problem, you come to know what exactly it mean. Okay, so we have some reflection points, and so that means let's say it is piston and cylinder oscillating. Okay, so we have to cut off some up to some place the mesh supposed to move here and move in the particular direction. So if you want to restrict that, then we specify the reflex plane. So up to that it will try to restrict, and after that it will stationary, and in one side it going to move in with the help of this frequency and amplitude. Okay, then you have moving body topo FV mesh. Okay, so with the help of this moving body topo FV mesh, what we're going to look at, we try to have some type of oscillatory class of the mesh motions. Okay, so it's more or less similar to this. Okay, so but this is specifically designed for some type of pumping or sinusoidal only. Okay, so here you have a linear oscillation, some flexibility, like you can add this different motion in this. Okay, so moving cell, face, front, back, front. Okay, so many different options we have to set, but this is how it going to look like. So this is in the broader sense this dynamic FV mesh, different setting that one has to take into account, that I club everything in one dynamic file. Okay, so if you want to look at different options, you can add up from this master dynamic FV mesh file and try to construct your own tutorials. Okay, so that is the idea behind that. Okay, so what we look at is inside this dynamic FV mesh motion, we have a couple of options like static, then solid body, multi-solid body, dynamic FV mesh motion, then dynamic inkjet, and dynamic refined FV mesh. Okay, so based on your requirement, you can adapt certain changes inside this dynamic FV mesh files and go ahead and simulate. But when you're simulating, you have to stick to the solver that have dym in their name. Okay, so either icodynamic form, pimple dynamic form, interdynamic form, okay, center dynamic form. So couple of dynamic form is available. So based on your requirement, you try to choose it and simulate your test cases. Okay, now let's explore couple of the tutorial based on this understanding.